Welcome back to the deep dive. Today we're jumping into something really fundamental from special relativity, using Audrey Mini's notes as our guide. Length contraction.
That's right. It sounds strange, but it's this idea that if you watch something fly past you incredibly fast, it actually appears shorter.
Shorter. How so? Like visually squished.
Well, not exactly visually squished in the sense of being crushed. It's shorter only along the direction it's moving. Think of it as a consequence of its speed relative to you.
Okay, but crucially, if the object could measure itself while moving.
Ah, yes. From its own perspective, in its own frame of reference, it's totally normal. Its length is unchanged. That's its proper length, dollars.
So Mini's example, an 8.6 centimeter object stays 8.6 centimeters for itself, even zooming near light speed.
Exactly. The object itself is fine. What changes, from your perspective as the observer watching it move, is the space it occupies, or rather, how you measure the space between its front and back ends. That distance appears contracted.
Right, the observed length, dollars later.
Mm.
But hang on, if the object itself is unchanged in its frame, is this contraction, well, real? Or is it just some kind of measurement artifact?
Oh, it's physically real from the observer standpoint. It's a genuine geometric consequence of space-time. And, this idea wasn't entirely new with Einstein.
Oh.
Well, Lorentz and Fitzgerald had proposed a similar sort of physical contraction earlier. It was a bit of an ad hoc explanation, really, trying to figure out why the Michelson-Morley experiment couldn't detect the Earth moving through the supposed ether.
Ah, the luminiferous ether. So they needed things to physically shrink to make the math work out for that experiment's null result.
Kind of, yeah. They posited a real physical squishing. Einstein later showed it wasn't some interaction with an ether, but a fundamental property of space and time themselves derived directly from his postulates, especially the constant speed of light.
And it pops out of the math, the Lorentz transformation.
Precisely. The link between the proper length and the length you observe, lava, is given by lava dollar. It's given by luppa. That gamma is the Lorentz factor.
The relativity adjuster. Gamma 1 squirt 1 V2C2. It pops up everywhere in relativity.
It does indeed, and it shows the length must appear shorter, and the amount depends critically on the speed, 5 $, relative to light speed, 5 $.
And Mini's notes stress something key here. Measuring the length of a moving object requires knowing where its ends are simultaneously in your frame, the observer's frame.
Yes, that's absolutely crucial, because simultaneity itself is relative. What's simultaneous for you isn't necessarily simultaneous for someone moving relative to you. Your measurement of the ends at the same time leads inevitably to a shorter length measurement compared to its proper length.
Wow. So the constant speed of light forces lengths to change depending on your motion, because it messes with our concept of at the same time.
You've got it. It's all interconnected.
Okay, theory is one thing, but is there, actual proof?
Absolutely. The classic example is atmospheric muons. The Rossi and Hall experiment is a famous demonstration.
Muons. Right, those were unstable particles created high up in the atmosphere, maybe 10, 15 kilometers up.
Correct. And they travel downwards very, very close to the speed of light. Now, the catch is they have an extremely short lifespan. Something like 2.2 microseconds on average when they're at rest.
So wait, if they travel near light speed for only 2.2 microseconds, they shouldn't get very far, should they? Maybe, 600, 700 meters?
Exactly. Classically, they should decay long before they reach sea level from 10 or 15 kilometers up.
But they do reach sea level. We detect them down here all the time. How?
Relativity provides the answer in two complementary ways, actually. We're focused on length contraction, so let's look at it from the muon's point of view.
Okay, riding along with the muon.
From the muon's perspective, it's essentially at rest, and its internal clock ticks normally, giving it that short lifespan. But the Earth's atmosphere is rushing up towards it at nearly light speed.
Ah, so the distance the atmosphere has to travel past the muon is length contracted.
Precisely. That huge 10 or 15 kilometer journey from the muon's frame shrinks dramatically. Because its gamma factor is so large, the distance contracts down to just a few hundred meters.
A distance it can cover in its short lifespan.
Exactly. It allows the muon to survive the trip to the surface. It's a direct, measurable consequence of length contraction. The other perspective involves time dilation for the observer on Earth, but the result is the same.
That's incredible. So for you listening, the big takeaway is that length isn't absolute. It depends on relative motion.
Yeah.
And remember,
it only contracts along the direction of motion. The dimensions perpendicular, like the height or width of our speeding spaceship, remain completely unchanged for the observer.
Which really drives home that space and time are interwoven into space-time.